Adeline Smart, and this is the automation of spot welding at L3Harris. L3Harris is among the top manufacturers of global defense and aerospace technology. The Tempe division manufactures light intensifying tubes, which are useful for customers such as the U.S. military who use night vision goggles in their day-to-day life. Operators working on the body component of these tubes are currently required to use a type of pen to make spot welds. The exterior of the body includes 3 metal tabs where the welds take place. Both the tabs and the nickel ribbons that are welded to the tabs are only a few millimeters thick, as shown here. Using the current weld apparatus, operators must make up to 9 welds per body, leading to excessive ergonomic strain as they perform the precise, repetitive hand motions. In addition, welding done by hand can cause unwanted material to splatter onto the tube, so operators must add a shield before making welds. Finally, the workbench was disorganized and contained non-value-added elements. A new semi-automated weld head was introduced to the area. With the new equipment, operators have to simply press a foot pedal and the machine will make the weld for them, decreasing ergonomic stress and eliminating the need for a shield. The tasks I focused on were updating the work instruction, deciding how to best arrange the workstation, and determining the optimal weld parameters. To update the existing work instructions, I used detailed technical language to describe each step of the new process. I also added images to provide the operators with visual information. The images here are an example. This is the emergency stop in each of its possible modes. For the workstation layout, I utilized the analytic hierarchy process and gathered statistical evidence to support a decision. I considered 4 layout options. The criteria selected were process lead time, wire management, safety, welfare, social concerns, and environmental concerns. After assessing each option with this criteria, statistical evidence pointed to option 4 being the most optimal choice. Finally, there are 9 variables on the welding equipment that can be adjusted to produce various types of welds. The best combination of these parameters, or the most optimal weld recipe, had to be determined through experimentation. My colleagues began testing this past spring and settled on a recipe, but revisiting that recipe this fall revealed new issues with sticking and sparking. I conducted new rounds of testing this fall, focusing specifically on minimizing these issues. I created a new data collection sheet with much greater detail, and then I spent weeks manually isolating each of the variables to understand how each one affected the quality of the weld. I input this testing data into Excel and created a system to rank the quality of each weld experiment. Finally, I added all the data and rankings into Minitab to generate interval plots for each of the 9 variables. These are 2 of the 9 interval plots generated in Minitab. These plots revealed the setting that produced the highest quality weld for each variable, and therefore determined the new optimal weld recipe. Comparing the fall and spring recipes demonstrates a significant improvement in quality. Even with complications, I have accomplished the main goals I set for myself with this project. I experienced setbacks with the hardware malfunctioning and having difficulty keeping team members on the same page at times, yet I was able to mitigate and learn from these risks and still provide completed deliverables. If I were to expand on this project, I would collect additional data for determining the optimal weld parameters. I appreciate the opportunity to learn from the Spot Weld project and the people at L3Harris. Thank you for